42 slides. This is now we are. Why is it worse? It doesn't. I'm not sure it will control it. It does. Best I can do.
Yes. Well, good afternoon. My name is Olga Dmitrieva, and I don't know, which screen do you prefer? Because I mean, we spent a lot of time over there, so let's exercise the muscles. Let's do that.
Good thinking.
So I came from Colorado, and the company I'm working for, Lessons, I'll just say a couple of words. Lessons been investigating the cold fusion for the last 9 years. And the project that I will be talking today, I've been working on this for a little bit more than a year. So that will be the numerical simulations and what we can do with those things. I won't be talking about how to simulate or how to model the cold fusion. And I want to say it right up front. What I will talk about is how the quantum chemistry methods can help us to better understand the environment, the chemical environment, which can potentially trigger the cold fusion event. So why is that? Because you've seen this morning presentations. It seems like we are deep in the field of the material science. So better we understand what we're making, what we're fabricating, hopefully better chance we have in the area of replication of the results. So I will be answering 3 questions. Why do we do those simulations? What exactly do we simulate? How we do this? And then I decided to spend a little bit time on the theory because I've been presenting some of the results in July in Missouri, and I didn't talk about DFT, which is a density functional theory, at all. I just totally omitted the theory and jumped to the results. And I think we owe the DFT a little bit of our time and effort trying to understand what exactly is it capable for. So I'll show you how the evaluation of the software is done, and then at the end I will show you just one example what the DFT can do. So why? Why do we want to use numerical simulations? I already sort of mentioned that. We want to better understand. We want to study the important parameters. Numerical simulations can also help us to save time and resources because we just use the computers instead of making each and every single alloy and then going through those exhaustive experiments. If we can understand what exactly is happening to our materials, maybe we can, through further optimization of important material parameters, actually enhance the effect that we're looking for. So what do we study? We can study multiple things. But for example, hydrogen, deuterium absorption and absorption conditions, because we know the material needs to be loaded. We can study the surface morphology, crystallography, and chemistry, the reactions that happen on the surface. We can monitor the change of the physical, well, measurable properties of materials, palladium, for example, nickel, alloys, and I'm talking about magnetism and electrical conductivity. So how we do this? For the last 40 years, it was an amazing breakthrough in the quantum chemistry computational field. And the big credit goes towards the density functional theory. And it's been acknowledged by 2 Nobel Prizes. So one is just recent, 2013, that was for developing the computational methods that can help to calculate the complex chemical reactions. In 1998, Walter Kahn has got the Nobel Prize for developing density functional theory. So that's next 6 slides, theory, so bear with me. What do we study? We study atoms and the electrons. What would be the straightforward method to look at those systems? Schrödinger equation. But we have, I mean, each palladium atom, just think about it. It has 46 electrons. So if we want to look at the playing ball, the amount of particles we have to calculate for will be in thousands and 10,000s. And so that will be the Schrödinger equation, which we can formulate, but it will describe the many-body problem. And I mean, Schrödinger equation is a powerful tool. It gives you the solution, the wave functions, then you calculate the observables, and you know the answer to pretty much any question you want to ask. But it works when the system contains of, well, 2 electrons, and beyond that, we're running into the trouble very fast because we need to solve for the 3 n dimensions. So the beauty of DFT is that it finds a bridge how to solve this problem precisely. It's not approximation, but it's just exact solution by using the system of the Kahn-Sham equations for single non-interacting particles. So right now, instead of all those interacting particles in the potential, we're looking for the well, I'll wave my hands if you guys don't. So we're looking at those non-interactive particles in the effective potential, and now we solve only for the 3 dimensions. So immediately we have a tool which we can load to the computer and start solving. But who says we can do this? So there's exactly two theorems which explain why this approach is valid. So the first theorem says the ground state properties of a many electron system are uniquely determined by an electron density. And I'm sorry, I didn't mention when I was on the previous slide. Now we solve not for the wave functions, but we solve for the electron density. How can we do this? So the ground state properties of a many electron system are uniquely determined by an electron density. How do we make this step? How do we make this conclusion? The thing is, the electron density defines the potential. Potential defines the solution of the Schrödinger equation. And the solution of the Schrödinger equation is a wave function, which means there is one-to-one mapping between wave function and electron density. So, sure enough, we can do this. But, so now we're solving not for the wave function, but for the electronic density. What density? Any density? No, and for this purpose, we use the theorem number 2. There's only one unique density, unique solution of this problem. And electron density that minimizes the energy of the overall functional is the true electron density. So the ground state energy has a corresponding electron density. So that is our solution. And you probably noticed, I used the word functional. So finally, what is the functional? For those who never heard of functionals, probably the easiest analogy will be function. So there's an argument and there's a value of function. Functional is, I guess, well, I'm going to say this. It's sort of a function of a function. So the good example would be the definite integration operator right there. So we've got our first sort of formula. Now we can go back to those theorems and write down the equations. So the first equation about the energy be a functional of a density, you can see. So the energy functional is the sum of the functionals. First term describes the interaction between nuclei and electrons. Second one describes the kinetic energy of the electrons. The last one describes the electron-electron interaction. So how can we rearrange those terms? We will talk about the potential that describes the nuclei and electron interaction, and then everything else, all other interactions, will go into this term. So then, according to the second theorem, we just minimize this expression and we get our true electron density. And everything would be peachy keen if we would know the exact form of this functional. So yes, to close the gap between many-body Schrödinger system and Kahn-Sham equation, we need to know the explicit form of that exchange correlation function. And we don't know it. So that's where the approximations came to the picture. So even though the theorem saying that we can find the exact solution which will totally match the Schrödinger equation, we practically cannot because we don't know what that functional is. So the approximations, how do we choose which one do we want to use? And there's many. So for example, the famous LDA, low density approximation. The next level up is generalized gradient approximation, GGA. The thing with numerical simulations and modeling is always, it will give you pretty much any answer you want. So you have to always come back and check with the experimental data to make sure that do those sanity checks. So it depends on what kind of a system you're dealing with. It's becoming an art. How do you choose those approximations? How do you choose which functionals are you using? And if any ever get involved with the DFT codes, then there's one more thing you probably will encounter, and that is pseudopotentials. What are those? I already mentioned palladium, 46 electrons. Do we really need to account for each of those electrons to solve the problem? Most of them, well, exactly 36, sit very close to the core. And they don't really want to even interact with anything else. So only valence electrons, that's what's important, and that's what we want to account for. So we can sort of substitute our wave function, which oscillates very close to the core, and our potential with some pseudo wave function. And pseudo potential, that's this red line, which will act exactly like the real one outside of the cutoff radius. So is it valid approximation? You know what, believe it or not, it is. For the chemists, absolutely. Very critical question, what DFT can and cannot predict. So let's start with what it can predict. The electron density, obviously, because it solves for the electron density. Total energy, ground state energy, lattice constant, bond length, vibrational phonon frequency, absorption energies. What it cannot do, since we're solving for the ground state, it cannot really predict excited state energies. It doesn't solve for the wave functions. We can't do the electronic transport. We can't solve for the band structure. But with some certain approximations and using other methods, those numerical codes, software packages, they actually solve for all this I just mentioned, including Fermi surface, density of states, and transport, the electronic transport usually solved with the green, well, anyway, green function. So, now we sort of covered the theory, and I did it in a very simplistic way, so I almost feel guilty. But but I was preparing this presentation, I think I actually started understanding it myself. So I don't know. Our expert on DFT can probably find a lot of flows, but I did my best. So if you give me a second, we'll look at the evaluation part. Evaluation, how do we know that those equations and computer codes really do the job? So we're working with palladium. What are we interested in? We'd like to see if the DFT can predict the palladium lattice parameter. We want to see if we start pushing the hydrogen in, it will expand. We want to see that the absorption energy of the hydrogen on the surface also matches the real numbers. And surprisingly, that was Peter's idea. He told me we can't move forward if we don't do the calculations on this just simple constructions, which is hydrogen molecule, palladium hydride, and palladium dihydride. And believe it or not, the DFT chemists, they know this very good. It's an extremely challenging problem. That is the problems which, with which DFT has a lot of trouble. Why is that? Because hydrogen, I mean, any of those molecules, there's a lot of interactions between, and that all that goes to that exchange correlation function, which we don't know. So that is challenging. Still, that is the results of my calculations, which is in red, and the reference. And you can see that's how the binding energy was calculated. So I've been just constructing those potential energy, excuse me, plots, and probably you can see yourself, you can just compare the numbers. Numbers match quite well. That was the interesting exercise. This is palladium dihydride, and there's two stable states when the two hydrogens are far from the palladium, and when they're closer. When they're closer, they're separated, and Peter is calling this the Barney air, right? And the Mickey Mouse air. So I have a question: is that a legit term? Can I even say it in public?
That's the correct scientific term.
Don't believe it.
I got something in my throat. I got something in my eye. It's a disaster. And I have another 20 slides. But anyway, so I'll try to maybe speak less. But so yes, that's the calculations done with quantum espresso. It does relatively matches the references. All of a sudden this plot becomes messy. Why? Because I use difference to the potentials. So each color is a difference to the potential. So you've seen those, that slide when I was talking about pseudopotentials, and when we just sort of combine the core electrons and yes, using different functional approximations, you can get a different result. So, okay, that goes back to me saying we have to be careful, because we can get a bit different results. So that's why we always come back and check with experimental data. The lattice parameter calculated for palladium, palladium hydride, nickel, nickel hydride. And you see blue is the numbers I've got, and red is experimentally measured, available, go to Wikipedia. The match is within 0.1 angstrom. Absorption energy. What is the energy of the hydrogen absorbed on the palladium or nickel or any other surface? So those calculations be done for palladium, platinum, copper, nickel. Once again, blue calculated, red is experimental. The numbers are accurate within 0.2 electron volt. So we're close. And for those purposes, I evaluated two packages: Quantum Espresso, which is open source DFT software in Amsterdam Density Functional, ADF, which is a commercial code, DFT code, and I had it for 1 month, so really enjoyed it. So finally, the most exciting part, the real exercise. So in ICCF 18, I talked about how the impurities and some defects in the near surface can affect the processes on the surface. How do we even pick up that subject? If we look back for 25 years of experimental data now available, the cold fusion, you can kind of see those points which seems to be important. For example, the high hydrogen deuterium loading is important. The defects in crystallography on the surface plays a role. You can't argue with that. Impurities and some etching of the cathodes also seems like do something, and in fact, the result is a duplicated cold fusion event, or is it a dead material? So, and from all those three, there are different properties that we can calculate or look at, and that's what I included in the ICCF 18 6 months ago. I sort of talked about that. That's what I'm currently looking at, and there's one particular example, which is probably somewhere here, between those two squares. That's what I'd like to talk about today. This is effect of edge on exposed crystal planes on the surface. Arik was showing us the pictures this morning, and he was showing us the pyramids. The same picture, the pyramids on the surface of the cathode. How do they form? And are they important? And is it important that it's pyramids, or should it be something else? Vittorio Violante mentioned the importance of 100 plane, crystal plane orientation, and its importance in successful Leonardo applications. The cathode fabrication is a multi-step process, and it goes through the etch, annealing, the crystal grows, the crystal grows, and then we etch. So this is one of the cathodes that we made at Coalescence. And you can see how rough the surface is. So this is the SEM image. And this is another representation of those pyramids that Arik was talking about. That is Colorado pyramids, it's not the Missouri pyramids. So we can see that the different crystallographic planes are exposed by the edge, but how come one are exposed and not another not? Why the edge etches these crystal planes, but it doesn't etch the others? Yes, so what we have for the palladium, we have, well, this is 3 low index planes, which is 100, 110, and 111. And that is the surface that's been modeled, the edge surface. So somehow the chemistry decides what is it gonna look like, and how does it decide? In 2013, in the Journal of American Chemistry Society, there was an interesting paper, and it was about the control of the palladium, control etch of the palladium nanoparticles. So what people looked at, they looked at the palladium nanoparticles cube, looks familiar, and it's been etched in the bromium solution. And the thing is, the bromium wants to stick to this plane, and that's what blocks the edge. So the edge goes only through this corner. So is it possible to solve the same problem, but now numerically in the DFT, and get the answer why the edge works in this peculiar way? So I set out the study. So I'm looking at these 3 different crystal planes, and I actually decided to expand it. So now I'm looking at the more halogens. And I have included chlorine because, for example, Mike McCoubrey is talking about poisoning the cathodes with HCl. So I wonder what chlorine has to do with it. So what you see on this picture is this 100, 4-folded side, and the iodide is sitting on top of it. What we're going to calculate for is absorption energy, where those halogens are want to stick. That's my 0. And this is a curves for each of those elements. So in lower, this is energy and slab orientation. 100, 11, sorry, and 110. So the lower the energy is, the lower absorption energy is, more stable the atom will be in that absorption side. That's where it wants to sit naturally. So you can see that for the bromine, it really wants to stick to 110 or 100. Yes, that's why it's been blocking the edge, because that's what it wants to be. If we're aiming for the really anisotropic edge, actually our choice will be iodine. See how non-symmetrical this thing is? So that may really produce an interesting features. Another important point, look at the hydrogen, blue line. So the hydrogen also prefers this absorption side or that absorption side. So there will be some competition between halogens and the hydrogen, the fight for good absorption side. So yes, that was a simple exercise, and you all probably can read the summary, so I'm not going to go through this. But it's a practical application. It's a relatively straightforward answer for which DFT is capable to give, relatively straightforward question for which DFT can give you the answer. And, well, believe it or not, this is the last slide. So, overall conclusions. So I didn't say anything about using the DFT for simulating the LANR. And I'm sure, if Peter wants, he may mention and say more. But as I already said before, we are in the realm of the material science. And those quantum chemistry tools can be extremely, extremely helpful if we are careful enough and patient enough. They can give us a perfect guidance explaining what exactly we're building and why the things work the way they work, even such as simple things as edge. So I am enthusiastic about it, and so yes, I guess I was spreading my enthusiasm for the last 30 minutes, and hopefully I have succeeded. So if you have any questions, you can shoot those questions at me now or later, whatever, please.
I'd like to offer a little suggestion.
Please.
I think you're on the right track, but you got to get out of the chemistry world and get into the cold fusion world. It's deuterium nuclei or deuterons that you got to get fused. You're talking electron theory, and electron theories in all the books, and not very much is written about positive ions like deuterons. They got, you got your one proton in there and a neutron, and it's not electron science. It's a deuteron science that you need to simulate in your simulator there, and then you got to worry about how they fuse and how they overcome the Coulomb barrier and that sort of thing. And on my talk on Sunday, I'm going to talk about this subject. So if you're in the chemistry world with this type presentation, I recommend that you look at more into the band states that you listed. You listed a nice four points that need to be covered, but you got to get into those from a cold fusion point of view, and then simulate that with your nucleus, with your numerical simulations. And I recommend looking at many codes that have been written for fission reactors, because the problems are very similar.
Okay.
And if you modified some of the codes that have already been written, you might get right into what you want to do.
Thank you.
Thank you.
So do you have a question or do you have the answer? If you have an answer, yes, you can talk.
I was gonna point out, Olga's actually already got a result, which is a highly non-trivial result. But if you'll allow me, I'll
Please,
share.
I actually got the slide I think you may want to talk about, right? Is that the one?
I can talk it up.
Okay.
So the question had to do with screening. So if you have two deuterons in a molecule, you sort of know the potential, you know how much screening. And we know in low energy beam experiments, there's a lot of screening of palladium deuteride. We also know that conduction electrons can do screening in the metal, right, like the Thomas Fermi. So I was thinking, since she was doing EDH2, which for the DFT is the same thing as EDD2, I thought, can we get our very first screening calculation? Can we take PDD2 and see if we can see the effect of the palladium on the screening between the two deuterons as our very first example? So I said, this will be fantastic. It'll be a big effect. If I can just calculate the parameters out, we have a quick paper out and everybody will be thrilled because this will be the first DFT calculation screening their palladium molecule, preparing for more complicated calculations in the lattice and so forth. So Olga ran 256
256 points.
a large number of points, and she set And she sent me the data, and, you know, I was busy in class and my administration was beating up on me and I was distracted. And it took, 4.5 months or some amount of time before I finally got to the data and I analyzed it. And I thought, this is gonna be great, I'm gonna get the screening, write a paper and have a good result. Analyzed all the data and I was stunned. I thought, this can't be right. That, the two deuterons in PDD2 experience, they're screened less with the palladium next door than they would be if they were just by themselves, which is a result I hadn't even dreamt in my wildest dreams that would occur. But that's sort of an initial result where it's beginning to impact our intuition. So the hope is to move towards getting palladium monovacancies. There's some talk about vacancies in the morning. And my hope was to see what the screening is between the two deuterons in the monovacancy as the next step in all of this.
I'm not saying that screening electrons aren't important, but I think they are block function screening electrons in the band state that you gotta look at to do what you're talking about. And that's what I recommend that you look into, is Bloch, Felix Bloch. He's in all the books.
Thank you. Go ahead.
Maybe I missed something, but does this take into account the type of crystal structure that's in the material? Like you got face-centered crystal, you got body-centered crystal. Does it differentiate between
Oh,
those?
absolutely.
So in this run,
Yes, that's what done
which
for
one
the
did you?
FCC.
That's, oh, okay, so.
Of course, nickel and palladium are FCC, so that's how you go in all those slices you've seen, they are unique for the FCC.
Okay, but, okay, but if you
configurations.
could get them.
And that's when I matched with lattice parameter. I mean, how else would I match it with the experimental data? Just knowing exactly precisely what the crystal is.
So you went to FCC, and if you did you try BCC approach on it?
Well, the BCC approach will give you different answer.
Yeah, okay.
And it will be really different, so you know that you are in some area where you're not supposed to be. Thank you.
We're gonna call it quits for today, so we can have coffee for tomorrow. I really apologize. The segue to come here took a little bit more time. And if we don't get the Cambros back, we don't get them filled. So on the hope that we can tank up for tomorrow and start at 9, which will be one floor below this. We're coming, I'm sorry it's so complicated, but for the rest